So just a couple of little notes just to make sure, because I kind of wrote things a little bit too fast and would have induced you in confusion. So so the question is, what was this dr doing there? Well, it just like slipped in. It's surreptitiously slipped in. There's no dr. We're not doing a volume integral. We're doing a surface integral. Okay. So this was a mistake. Please cross it out. The reason why there's an r squared here is, of course, that we're doing a surface integral on the surface of a sphere. And you remember, there's the theta angle, there's the phi angle. So the surface element at the surface is, r with the d phi. But then in this here, because of the cos theta, you have to differentiate. So there's a r sine theta. So the surface element is r squared sine theta, d theta, d phi. Okay, so that was just a little dr too quickly. You see, reflexes kind of work against you when you get old. Then the other thing, maybe you were confused with again my notation. So here it's really again the differential surface element. So this should just be a bold-faced A. Forget about the hat. I mean, it's not. There's no hat. I don't have a hat. It doesn't have a hat. You don't have a hat. Okay, then here again, maybe I went a little bit fast because I'm just using Gauss's law immediately, right? So here we just did the surface integral of E in the spherically symmetric case. Just got the size of the field times the surface, 4 pi r squared. But of course, by Gauss's law, this is just equal to Q over epsilon 0, which allows me to write the absolute value of E as Q over 4 pi epsilon 0 r squared. And that's how you get this, okay? So just to make sure you kind of get the reasoning, okay? So that's important points. Okay, now in the notes there are once again some examples. Yeah, so there's the example of the cylinder. There's also maybe one example that I'll do very quickly. It's the example of infinite planes. Okay, so maybe it's just, well, I should start by asking you, were there questions that came up during the break as to what we've just done, or is it kind of okay? It's coming back, is it? Yeah, Gauss, old friend. Yeah? Okay. He was a cool chap, Gauss, right? You know the story about when he was 8 years old at school? And no, so he was like you. He was talking all the time when the teacher was talking. Yeah. But at some point, the teacher kind of got fed up and knew that Gauss was into math and stuff, and said, "Oh, little Gauss, stop bothering me. Add up the numbers of from 1 to 100, and then talk to me." And then he said, 5,050. So, of course, you know the trick, right? You just do 1 plus 100, 2 plus 99, 50 times over, and you're there. So that was little Gauss. Yeah. But, what's the, no, anyway. Okay, so other examples here, if you have no questions. Cylinder, C notes. C notes. Okay. Then let's do the example of the infinite plane. Okay. With surface charge density sigma, so surface charge density sigma. Okay, so what have we got? We have this wonderful infinite plane that goes like this. Let's put it in the xy plane at z is equal to 0. So here I have a vector, z hat, unit vector coming out. So what happens? Well, maybe I should have drawn it a bit bigger for my thing. We want to know the electrical field in the vicinity of this infinite plane. So what do we do? Well, there's symmetry in this thing. What's the symmetry? essentially there's no xy dependence. If the plane is infinite, it doesn't matter where you sit. The only thing that can potentially matter is the z direction. Okay, but by translational invariance, anywhere within the xy plane, the thing should be the same. So how do we do this? So we want to calculate the electrical field. The solution, of course, we invoke Gauss. Okay, and what we will do is essentially consider a surface which I'm sure you've used this term before, a Gaussian pillbox. So when Gauss was very old, he needed to take like many pills, and he had this nice little pillbox, and then he would like, oh, you know, it's great. So what's a pillbox? It's just like a little rectangle thing, 3D, that you put straddling the surface, right? Like this. Okay, so again, with my wonderful talents of drawing, I can try to draw for you a pillbox. That's not good. So I would have a little thing like this, and then it would come down. Then it would go through the surface. And on the other side, I think you get what I mean without me drawing. Yeah? So, okay, so the pillbox has a little piece above the surface, a little piece below the surface, and it's very, very thin. I can make it very, very thin, just hugging the surface. Okay. So what we want to have is the integral over this Gaussian pillbox of E with the dA, the surface area. But now S is really all the surfaces of the pillbox. Okay? So this has, like, if you want, 3 contributions: the top bit, the bottom bit, and then the side bit, irrespective of the shape. Doesn't have to be a rectangle. Okay? And because I can make the pillbox as thin as I want, the contribution from the sides does not matter. Okay? The field is, you know, we don't take the field to be like transversely infinite in there, so this thing converges to a 0 integral. Okay, so here, so three contributions. There's the top, there's the bottom, and there's the side. And this one is just 0. Okay? When I take the okay, now the problem, of course, also has like a kind of inversion symmetry, right? There's no top or bottom. I can just rotate the thing, and the field, if it's of a certain value above, below it should just be minus the same thing, so that I preserve this inversion symmetry. Okay, so the field by symmetry, it must just be a field in the z direction. So it must be equal to some value E in the positive direction for z greater than 0. And it just has to be minus the same thing for z less than 0. Okay? That was a sigh. Yeah. Right? So now the full integral over the surface is going to be essentially just twice the value of the field near the surface like this with A. So A, this is just like the surface area of the pillbox. Of the top of the pillbox. Okay? Now the point is that the Q enclosed, the total charge, is just going to be the surface charge density times the area. Okay? So the two have to be the same. So therefore, E is just equal to, so Q enclosed over epsilon 0 has to be equal to this. Area falls down, factor of 2 comes in. So sigma over 2 epsilon 0. And now just the sign of the coordinate z, so that I can just write as z divided by absolute value of z, and this is in the direction z hat. Okay? So you see, we kind of put in some symmetry considerations in there, and we just obtained the value of the field. Okay? Does this look right? Question?
Where exactly is the factor 2 coming from?
Because, so I have here, so Gauss's law tells me that this is equal to Q enclosed over epsilon 0. Right, so Q enclosed over epsilon 0 is equal to sigma over epsilon 0, like this. The factor of 2 comes from the 3 contributions that we have to the surface integral. There's the top bit, there's the bottom bit, and there's the side bit. The side bit vanishes because my pillbox goes chunk. And the top and the bottom each contribute an equal amount.
Okay, yeah.
Because at the top, my normal vector is, my field is going this way, with normal vector just z hat. At the bottom, my field is going that way, with the normal vector to the surface being minus z hat. So minus z hat dotted into field going that way is this positive number, just absolute of E there. Same thing as the top. So I get twice the same contribution, which is two times the area with E. Right? Question?
What's the difference between Z and the absolute value of Z?
So here, what I mean here is that, so Z over absolute value of Z is just the sign of Z. I could write this as just, sign of Z. Meaning, +1 if Z is greater than 0, -1 if Z is less than 0. Okay, so that's the notation. So does this look right to you, this result? Because, what about the Z dependence on this? How does it depend on Z? Yeah, there's no sense of distance from the plane. It doesn't depend on Z. But does that make sense? Yes, because my plane is infinite, right? So indeed, the field of an infinite plane is absolutely independent of the distance from the plane. And the way you see this really is that if you put yourself a certain distance, you have the field lines coming from everywhere. The field lines are actually parallel to the z-axis. And if you go twice as far, you kind of pick up 4 times as much area, but you're twice as far. So the 1 over r squared picks up the same thing. So you see many more charges, but you're further away. But you end up seeing the same field. Okay? But it's a non-trivial reason why you're seeing the same field. If you were to tag the charges in your plane as to being the ones that influence you and the ones that don't influence you, this tagging would be a function of Z. But the total of the contribution does not depend on Z. Okay, so this is the correct statement here. And you see here, we don't have to do any complicated integrals or anything like that, just using symmetry, and then you can get it. Okay, so so there are further examples in the notes. Also, spherical shell, uniformly charged spherical shell. So examples 2.6, 2.7 in the notes. I will let you go through those again if you need a reminder of these, because I trust that you can apply these things. Okay. in the exercises that you'll do anyway, you'll have to use these things once in a while. Okay? So, now let's just do a little restart here. Continue with our refresher continued. Okay, so up to now, what we know is that the divergence of the electrostatic field is the local charge divided by epsilon 0. The curl of the electrical field just vanishes. We also know that we can write our E as minus the gradient of some scalar potential, V. Okay? So essentially, an immediate consequence of this is that we can write another equation for the potential, namely the Laplacian acting on the potential is equal to minus rho over epsilon 0. Okay? And this is Poisson's equation. Poisson's equation, number 2.49. Okay? And then if the charge density distribution vanishes, then we just get the equation that the Laplacian of V is equal to 0. And this is the Laplace equation. So, you know, Laplace really pissed off Poisson because Poisson wrote this general thing, and then Laplace said, we'll just put the density to 0, and then there's this other equation. And then people started calling it the Laplacian instead of the Poissonian and stuff like that. And they're mortal enemies ever since. But anyway, okay, so these are the two fundamental equations, okay? Like super important. And essentially, much of electrostatics is about finding solutions to the Laplace equation or Poisson's equation. Okay? So we can discuss that a little bit today. Yeah. Today I think what I'm going to do is, I'm kind of hesitant a little bit whether I should jump on this today. Maybe how much work did you already do with the Poisson and the Laplace equations? Did you see in the first year at least the Laplace and Poisson equation? Yeah? Yeah. And did you discuss conditions under which they are solvable? Namely, what you need in order to find unique solutions for these things. So? Yeah, so then maybe we'll get there. Okay. Anyway, so these are simple enough equations. They're of super fundamental importance. So why? Because we always like computing a potential, because a potential is a single scalar function. It's not a vector function like the electrical field. So in a sense, it's a more condensed representation of the information, if you want, that you need to reconstruct the electrostatic field. So typically, it's easier to compute these things. Okay. And preparation for the discussions about the uniqueness of solutions of these equations, we have to mention some things about electrostatic boundary conditions. Okay? And in the notes, this is on page 2.12. Okay, so so essentially, the example we just did from the example of the infinite plane with charge, with surface charge density sigma, okay, we can immediately generalize what we had done to a situation which is now in the presence of arbitrary other charges. Okay, just imagine a whole mashup of charges all everywhere, but here I've got a plane with a surface charge density sigma. Okay? And this plane might not be infinite, but what I'm doing is that I'm looking at the immediate vicinity of this plane. So in the immediate vicinity of this plane, my plane looks infinite to the little, coronavirus looking at the field immediately next to this plane. Therefore, I can reuse the result that we just did. So what I have is I have a big mashup of charges all over the place, yeah, everywhere. But here, I've got a charged surface. Okay, this is a charged surface. And I'm going to do, in this little point here that you barely see, I've got my pillbox, yeah, which is finite, straddling the surface. And the pillbox has a certain area, and it's just immediately in the vicinity of this charged surface. So I'm now measuring the value of the field on the upside of the surface minus the field on the other side of the surface, because I'm doing my Gauss's law integral form on this. So really what I'm using is the result that we just did, that in here, if you want, from a plane, if I cross a plane with surface charge density sigma, then the value of the electric field jumps as I cross the plane by a value of sigma over epsilon 0. In this particular case, because we have no other charges, it goes from minus 1/2 to plus 1/2 times, sigma over epsilon 0. But if I have lots of other charges, the field takes a certain value here. But then when I jump here, it has increased by a value of sigma over epsilon 0. Okay? So I'm just using exactly the same result that we just derived here in a more general situation. And now what I'm saying is that the electrical field above the surface and perpendicular to the surface minus the electrical field below the surface, and again perpendicular to the surface, that this discontinuity in the field is given by the surface charge density divided by epsilon 0. Okay? Now, of course, we've got one component of the electrical field, but we would also like to know the components of the electrical field along the plane. Okay? So for the component of the field which is parallel to the surface, what we will do here is just use a line integral straddling the surface. Okay, so again, let me just impress you with my drawing skills. So what am I going to do? I'm going to have like a line integral that goes like this, and then goes under the surface and comes back like this, like this. You see what I mean? Yeah, so I have my surface, and my line integral just goes roop, 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 roop. and comes back. Okay? And I will take this line integral again, just straddling the surface. So I'm doing an integral along the surface, then I'm just jumping under, coming back, and coming back up. Okay? So what I'm doing here is that I can do the integral over this kind of path here of EdL. Okay? But I know that this I can write by Stokes' theorem as the integral over the surface represented by this path of the curl of E. Okay? Here I'm invoking Stokes. So it becomes the integral over this surface here of okay? But, of course, this is 0, right? It's 0 because I just squash my curve. It has no surface, right? And the field, if it is finite, I get a finite integral. So unless the field is infinite, then, whatever. But the field cannot depend on the shape of my curve. Yeah? So therefore, the whole line integral has to be 0. And that means that the component of the field parallel to the surface has to be continuous. It has to be the same up and down. Because on the one hand, I integrate this way, and on the other hand, I integrate this way. So plus contribution, minus contribution, it becomes 0. Okay, so you see the reasoning? This just tells you as well, that the component of the electrical field, which is parallel to the surface, above the surface, is the same thing as the field parallel to the surface, below the surface. Okay? So in a proper notation, if I now compare the total electrical field above to the total electrical field below, I just get sigma over epsilon 0 with the normal unit vector to the surface. Okay, so this is the normal unit vector. Yeah, normal to the surface. Okay? So there's a discontinuity in the electrical field at a surface charge density. And the size of the discontinuity in the field is given to you by the charge density in this surface. Okay? Question?
Yeah, I don't understand the parallel part of the electric field because you said before that that's 0, right? Through the kilowatts, like the sides are 0.
In the earlier example, we only had the infinite plane. Now I'm doing a completely general thing where I can have, charges here and there that generate a field which is pointing in a certain way. And in addition, I've got my plane here, which is, it's not an infinite plane, it's just like a piece of paper. Okay? And I'm looking at the shape of the electrical field in the vicinity of this. So by superposition, of course, I've got the contribution coming from this plane, but I've got the contribution from all the other junk in the world. And that gives me a field that points somewhere. Okay? But now what I'm looking at is just the difference between the value of the field immediately above the surface that I have and immediately below. And that's it. And the only thing I can say is that the jump in the value of the field here between these 2 points is given by the charge density on this surface. About the mean value about E above plus E below, right? Then I need to know the rest of the charge distribution to tell you what that is. But if I look at the difference between above and below, it's only affected by the surface charge. So that's the slight generalization to the previous example that we did. Is that clear to everybody? Yeah? Okay. Question?
Doesn't 2.26 guarantee that any closed path integral of the electric field is zero?
Yes.
So could we have concluded it's zero regardless of how close the shape was to the surface?
The little so the whole thing is yes, but let's say that that's my plane, and let's say that your line integral, it goes like this. Okay, it goes like this. I know you get 0, but I'm not asking you the value of the field here. So of course, in the end, you will do the integral. You'll get a complicated number here. You'll do this integral going somewhere else, yeah. And you'll get minus the same number, but that still doesn't tell you exactly anything about the value of the field here. If you want to know the field here and here, it's better to focus your line just on this thing. So then the contribution to the integral is fully defined by the value of the field in the immediate vicinity of the surface. Do you see what I mean? Yeah, because what we want to measure is really this E above and this E below, which is here, not here. We want it here. So that's why we do the integral here. But I agree, the other integral is also 0. It's 0 for all curves.
Those integrals always zero. How do the information out of the special case that just
Because essentially, in that case, you know, so the value of the integral itself, if I write it down as a function of E above parallel and E below parallel, the value of the integral is equal to E above parallel minus E below parallel.
Okay.
Yeah?
Go through the expressing integral even though it doesn't matter, and then conclude what the parts are.
It's expressing the 0. I know it's 0, but the 0 is represented as the difference between the parallel to the plate electrical field above minus below. So it is 0, but it's not, you know, if you know where electrostatic fields come from, of course you immediately tell me, yeah, of course it's 0, because there's no like disequilibrium of charge between left and right here. So by symmetry, there's, and I say, but look, I mean, you know, I'm kind of, I've got this like strange shape here. I'm not telling you it's an infinite surface or something. I'm telling you it's a surface. The surface can be like this. Huh? My poor notes. But still, for this surface, I can put myself, you know, really, really close to the surface until it starts looking like an infinite plane. And then at that region of space, I can determine what the electrical field looks like. So this is a statement, really, by E above and E below. What I mean is the limit, as the distance goes to 0, of the field at the plane plus epsilon or at the plane minus epsilon. Okay, so it's almost, if you want, this is almost like the differential of the field with respect to position around the plane. Okay? That's the idea. So if you want, as a function of this coordinate, the charge density is a delta function in this coordinate. Okay? So that's why you get this. Okay? Right. Before I rip up my notes any further. Okay. So, yeah, that's the kind of proper way of writing this, this condition here. And this is equation 2.54. Okay, and then so the field is discontinuous. Okay. the potential so if I look at the potential difference between above and below, I would just do the integral between the two. So V above minus V below, that would be the minus integral from, well, I guess, yeah, A to B, but now A is below and B is above. Doesn't matter, you'll get the idea. E dl. Okay, so what am I doing now? I've got my plane, and I'm just integrating over a tiny, weeny, itsy bit that just goes through the boundary. Okay? But you see, this integral here, this line integral, I can make as short as I want. Okay? So there is no contribution from this thing. This is zero. Okay? So the potential is continuous. Across the surface. Okay? So what happens? The field has a jump. So if you plot the field as a function of the z coordinate here, has a jump. But if you look at the potential is continuous. But the slope of the potential has a discontinuity. So the potential has a cusp. It's continuous, but it has a cusp given by the charge density. And it's easy to write down because the only thing that we have to do is use the representation of the field in terms of the potential. So it has a cusp, namely that the gradient of V above minus the gradient of V below. That's just the same equation as before, but now with a minus sign, right? Minus sigma over epsilon 0 n hat. Okay, this being a vector, right? So remember, this is a vector. Okay, so that's what happens at one of these, boundaries of the field. Okay, and let's see where we're at. Okay. Yeah. So maybe just so if you want, so in terms of the derivative normal to the surface, okay, so the dv above dn minus dv below dn is equal to minus sigma over epsilon 0. Okay, what I mean with n here, it's the coordinate going, normal to the surface. Okay, so if my plane is in the xy plane, then the n is just z. But if my plane is, in the yz plane, then the normal is just x. And if I'm somewhere in between, that way, that way, that way. Okay? That's what I mean. So the if you're looking at the spatial dependence of your potential as a function of this coordinate that goes normal to your surface, you have this cusp. Okay, like this. So these are conditions that we'll use later. Okay, so I didn't have the time to do conductors, but I guess you already know the important things here. Conductors, you know that the conductor is an equipotential and things. Please read through the notes for a refresher. But I mean, I think we'll just like view that as already known stuff. I will just use it later in what we do in the next session. Are there any questions before we leave, or? Huh? Okay, very good. Then I'll see you next Tuesday.